Hello students, welcome back. Today we will discuss about some problems in electrostatics. Here there is a system of charges and to find the net force acting on any charge due to system of charges. The question that is 5 point charges each of value q coulomb are placed on 5 vertices of a hexagon of side length L. A charge minus q is placed at the center of hexagon. Find the net force acting on this charge minus q. You know that according to Coulomb's law, force acting between two charges, it is directly proportional to the product of the charges and inversely proportional to the square of distance. So due to each pair of charges, the force acting on charge minus q placed at center is F is equal to kq square by L square. See, side length is L, hexagon it is, so distance of each charge from the center will be also equal to L. As in the hexagon, each angles here which will form, that will be 60 degree, and that's why it will be an equilateral triangle. So whatever the side length, that is the distance of each charge from the center. So various forces which are acting on charge O, that is, you can say due to charge A as positive, negative, so it is attractive force acting towards A. Due to charge B, it is acting towards B. Due to charge C, it is acting towards C. Due to charge D, acting towards D. Due to charge E, acting towards E. Out of this, these two forces, they are in opposite direction. Resultant of these two is 0. Again, these two are also in opposite direction. Resultant of these two is 0. So these two effect is cancelled. These two effect is also cancelled. So resultant is only because of this component. What is the value of this? That is kq square by L square, and it is acting along the direction of C. So we can say the magnitude of force is kq square by L square Newton acting along vector OC. Okay. So this way you can find the force acting on any charge due to system of charges. Here another example is to find electric field due to system of charges. Here you can see it is a pentagon of side length L and 4 charges each of magnitude q. It is placed on vertices A, B, C and D of pentagon. Question that is to find the resultant electric field at the center of this pentagon. Now say, for a pentagon, if you measure the angle between two consecutive points with respect to center, this angle will be 120 degree. 120 into 5, that is 360 degree total. Now, if on all vertices, if charge q is there, then total there will be 5 value of electric field. All are into different direction. So due to charge A, electric field, this is the direction. Due to charge B, electric field, this is the direction. Due to charge C, electric field, this is the direction. Due to charge D, this is the direction. All these are shown with dark lines. If on vertices E also, if charge q is there, then electric field due to that will be along this direction. It can be along this direction. Now, all these 5 field directions, you can see they are at an angle of 110 degree with respect to each other. All are, we can say, co-initial vectors. So resultant of all this will be 0. So we can say that if charge q is placed at this point, resultant field if it is 0, it means that if charge q is not here, then the resultant of remaining 4 electric field vectors should be equal to the magnitude of electric field due to the charge placed at point E, and its direction is equivalent its direction is opposite. So, due to, if you consider charge Q, if it is here, then due to this charge Q, what is the value of electric field? It is kq by L square. kq by L square. If charge Q is here on this point E, then electric field due to that is direction from E to O. So we can say that if this charge Q is not here, then resultant of this remaining 4 electric field will be equal in magnitude, opposite in direction. So we can say resultant electric field is kq by L square acting from O to E. So acting along direction O to E. So this way you can find the resultant electric field due to system of charges. Another equation. Two equally charged identical spheres A and B. Identical sphere A, sphere B. Repel each other with a force of 2 into 10 raised to minus 5 Newton. If they repel, it means that charge on both equal, that is, let's say Q, and the value of this force F is equal to, if the separation between these two, if it is R, then case Q square by R square, that is equal to 2 into 10 raised to minus 5 Newton. Another identical uncharged sphere C is touched to A, then placed at the midpoint between A and B. So charge on A, it is Q. Now when another sphere C is touched to A, identical it is, so the charge becomes Q by 2. B, it has charge Q. C is placed at the center, on that also charge is Q by 2. This separation is R by 2. This separation is also R by 2 now. Now, the force acting on C, question is, find what is the net electrostatic force on C. So first of all, how many forces will act on C? One is due to A, another is due to B. Both the forces are repulsive. So we can say force acting on C due to A, this is the direction. Force acting on C due to B, this is the direction. So both the forces are in opposite direction. As they are in opposite direction, resultant force will be the difference of their magnitude. So let us first find the magnitude of each force. Force on C due to A. Force on C due to A, that is K Q by 2 upon R by 2 whole square. So that is, see, here also 2 square, here also 2 square, so it is KQ square by R square. Force on C due to B. Between these two, how much force it is? So it is K Q by 2 to Q R by 2 square. So this is equal to, see here single 2 it is there, here 2 square is there, so that 2 goes to numerator, it becomes 2 times KQ square by R square. You can see the magnitude, this force magnitude is just double compared to this, and that's why the resultant of this 2, it is always in the direction of bigger force. So the force will act in the direction from C to A. The net force on C is F on C, that is FCB minus FC. This is 2KQ square by R square minus KQ square by R square. So that is equal to KQ square by R square, and the direction is from C to A. So acting along vector C. As it is a force, you can write the unit Newton. Say kq square by r square, what was the value? It is 2 into 10 to minus 5. So again same resultant force is same, so you can write this is by 2 into 10 to minus 5 Newton along C. Next question. A conducting rod of negligible thickness and length L carries a total charge Q which is uniformly distributed over it. Determine the electric field at any point located on the axis of the rod at a distance d from the nearer end. Show that the rod behaves as a point charge for faraway points. Consider this is a rod of length L, negligible area cross section. Charge Q is distributed uniformly over it. Let's say positive charge is there. Electric field due to positive charge is radially outward. So if you want to find the electric field on the axis of this rod at point P, direction will be outward. Distance of point P from the nearer end of the rod is d. Length of the rod is L. Now, to find electric field we need distance and the charge. Here charge Q is there, but its distance from point P, if you want to say, see charge Q is distributed over this whole length L, and that's why we cannot consider it as a point charge. Okay. Here we have to consider this as a continuous charge, and that's why to find the electric field due to this charge distribution, let us divide this whole rod into small elements each of length dx and find the electric field due to each element dx. First of all, as charge is distributed uniformly, we can say linear charge density represented by symbol lambda, that is total charge divided by total length. Here, as it is uniform charge distribution, so for small element of length dx, if charge on it, if it is dq, then lambda is also you can write as dq by dx. Now for this element of length dx, its distance from point P, if it is x, then electric field due to this charge element dq is k into dq by x square. Value of k is 1 upon 4 by epsilon naught. Dq you can write from this relation, dq is equal to lambda dx, so you can put lambda dx upon x square. If you want to find electric field due to whole rod, you have to integrate this electric field. See here only one variable in this equation, that is x rest of all is constant, so you can integrate over the length, and to integrate over the length you can write from element C. If you consider the element at this end, its distance from point P is d, element at this end its distance will be d plus L. So different elements, their distance ranging from d to d plus L, and that's why to integrate from the range d to d plus L, lambda upon 4 pi epsilon 0, that is constant, integration of dx upon x square, and integration of 1 upon x square is minus 1 upon x, and that's why the range of integration when you put d to d plus L, you can simplify. Its final limit minus initial limit, negative sign is there, that's why 1 by d minus 1 upon d plus L. So taking cross product, you can write the result, that is L upon d into d plus L. Lambda into L is the charge Q, so if you write this as lambda into L upon 4 pi epsilon naught d into d plus L, 1 upon 4 pi epsilon 0 is k, so k lambda L upon this, and this lambda into L, that also you can represent as symbol Q. Now, if this distance d is much larger compared to the length of this rod, we should show that the rod behaves as a point charge for faraway point. So if d is much larger compared to the length of this rod, then in that case L is neglected, d plus L almost equal to d, and that's why equation becomes k lambda L upon d square. Now lambda into L this quantity will give you charge Q, and that's why it is kQ by R square. And this is nothing but the equation of electric fluid to a point charge. And that's why we can see that for a faraway point on the axis of this rod will behave like a point charge.